Standard databases are excellent at retrieving facts, but when a problem requires weighing human values, subjective priorities, and conflicting constraints, standard data retrieval structures collapse. They can give you the numbers, but they cannot tell you what those numbers mean for your organization. To solve for subjectivity, we build a decision support system, or DSS. A DSS is an evidence-based recommendation engine. It takes chaotic variables and structures them into an organized set of requirements. It does not replace the human decision maker. It augments them, ensuring the final call is mathematically defensible. Looking at this three-component architecture, the first block is the data management subsystem. This is the intake valve. It extracts, transforms, and loads raw, multi-format data from external sources and prepares it for processing. The data then flows into the model management subsystem. This is the analytical core, where mathematical, statistical, and simulation algorithms run calculations on the cleaned data to score and rank the possible outcomes. Finally, the user interface translates those calculations into readable dashboards. Anchoring all three of these blocks together is the knowledge base, a central repository storing the specific business rules, expert preferences, and constraints unique to the organization. A functional DSS requires all of these components working in tandem. Remove one, and the system fails to translate a subjective human dilemma into a deterministic, computable output. Consider two opposing engineering targets. On the left, we have a corporate business case. PT Maju Bifama needs to select one optimal manufacturing supplier from a pool of 20 active candidates. The constraints here are heavily qualitative. Evaluating reputation and service requires subjective judgment. If left to a manual process, this decision is highly vulnerable to human bias, undocumented assumptions, and conflicts of interest. On the right, we have a government case. The local social services agency, Dina Social, has a strict budget to distribute welfare aid to exactly 5,000 families, but they have 50,000 applicants. In a manual environment, reviewing 50,000 applicants is a 3-month process prone to human error and inconsistent application of the rules. The sheer volume of flat data requires a system that can provide objective, high-speed processing. Despite these contrasting requirements for scale and subjectivity, the engineering teams for both projects must follow the exact same 6-phase software development lifecycle to build their systems. The geometry of the data, its volume, and its subjectivity must dictate the specific engineering choices made in the upcoming phases. Phase 1 is planning. Before a line of code is written, the core problem is defined and subjected to a rigid feasibility study. We have to prove the project is actually viable. This analysis spans 4 dimensions: technical infrastructure availability, financial return on investment, operational user readiness, and time constraints. If the project fails on any axis, development stops. Once cleared, we move to Phase 2, requirements analysis. Here, engineers draw a strict boundary between functional requirements, what the system actually does, and non-functional requirements, how the system behaves while doing it. Functional requirements are the tangible actions. The system must ingest multi-format data from APIs and spreadsheets. It must allow users to adjust criteria weights and immediately test what-if scenarios on the dashboard. Non-functional requirements are the operational limits. The system must return calculations in under 2 seconds. It must support 50 concurrent users without degrading, and it must maintain 99.5% uptime. Failing to map strict operational limits early guarantees failure. A brilliant algorithm is useless if the server times out before it can deliver the answer. Phase 3 is system design. This is where the architecture takes shape, specifically focusing on the selection of the model management algorithm. The analytic hierarchy process, or AHP, provides mathematical rigor for subjective decisions. A hierarchical tree breaks the goal into sub-criteria for pairwise comparisons. To prove the human logic is sound, it calculates a consistency ratio. If higher than 0.1, the system rejects contradictory weights. But if you apply AHP to the government welfare case, the system would collapse. Pairwise comparing 50,000 citizens against each other would require billions of manual matrix entries. Instead, the government case requires simple additive weighting, or SAW. SAW is engineered specifically for massive, flat, objective scoring. By assigning direct percentages to standardized metrics, SAW executes rapidly and linearly. It skips the complex expert matrices entirely in favor of raw computational speed. Algorithms are not universally good or bad. Their validity depends entirely on matching the mathematical structure to the geometry of the data. Phase 4 is implementation. We take the architectural blueprints and translate them into executable modular code. To see how this works in practice, let's look at the core mechanics of SAW. The first mathematical hurdle is scale. You cannot directly compare a monthly income in the millions against a household size of 5. The data must be normalized. Look at this pseudocode. For benefit criteria, the system divides the citizen's value by the maximum value, compressing raw numbers into a decimal between 0 and 1. For cost criteria, the math inverts, dividing the minimum value by the actual income. With all variables normalized to the same scale, the algorithm initiates the second step, weighted summation. The normalized values are multiplied by strict criteria weights, like 35% for income. These fractions are added to produce a single definitive score. The output is a strictly ordered ranking. The candidate with the highest numerical score is mathematically verified as the most eligible for aid. SAW takes chaotic, multivariable human realities, strips away the noise, and flattens them into standardized output. Phase 5 is testing. Code compiling successfully is a baseline requirement. It does not mean the system is structurally valid. It must survive 3 layers of testing. First is unit testing. Developers isolate individual functions, like the SAW normalization math we just reviewed, and feed it dummy data to ensure the localized output is flawless. Second is integration testing. This verifies the architecture as a whole, ensuring data flows correctly from database to model algorithms and to the user interface without corruption. Finally, user acceptance testing, or UAT. The system is placed in front of actual decision makers. They run real-world scenarios to validate that the UI is intuitive and outputs align with their expertise. This testing gauntlet ensures the mathematical model accurately reflects reality before it is ever allowed to impact human lives. Phase 6 is evaluation and maintenance. After deployment, we do not rely on subjective feedback. We mathematically prove the system's success. We track 5 specific metrics on this dashboard. Model accuracy must hit 85% or higher. Response time must stay under 3 seconds. The system needs a user adoption rate over 70%, a system usability scale score of at least 70, and downtime cannot exceed 4 hours per month. Applying these strict engineering standards yielded clear results for both projects. In the corporate case, the AHP model bypassed subjective bias entirely, identifying supplier B as the optimal vendor with a winning score of 0.412. For the government case, the SAW model successfully ingested 50,000 records and cleanly isolated the top 5,000 citizens eligible for welfare. By replacing the manual 3-month review cycle with this automated process, processing time fell to just 3 days. Furthermore, the algorithmic consistency of the SAW model reduced the rate of mistargeted aid by 60%. A correctly engineered DSS provides an immediate return on investment by systematically eliminating processing bottlenecks and filtering out human bias. Getting to those results requires choosing the right path. Selecting a development methodology is just as critical as choosing the algorithm. The linear system development lifecycle works best when requirements are completely locked, while an agile approach allows for rapid, iterative adjustments. For high-stakes decision systems, a hybrid approach often works best, combining strict algorithmic safety of linear documentation with the flexible, rapid prototyping of user interfaces. But no methodology can save a flawed premise. The output of an algorithm is only as reliable as the quality of the data fed into it and the mathematical alignment to the problem space. The purpose of a decision support system is to resolve the complexity of competing variables and constraints. It builds a foundation of objective evidence, but the human user must always take the final action.